Good morning, everybody. Who of you has seen this display just right in this building in front of the elevator? I saw this and thought, this is so great. This is such a great energy interface, because somehow the elevator is also an electric vehicle, somehow, right? But let's dive into the topic. Energy interfaces are a common built-in feature in electric vehicles. Here we see three different. One represents somehow the technical system. One displays displays the amplitudes of energy power, and on the right side the trace display that also Thomas has already introduced, that allows to compare energy consumption with maneuvers or situations from the past, and which of these three is best. But first, important to say is that eco-driving is a central challenge for human-car interaction, and it's important to support humans in eco-driving because it has several advantages. On the individual level, it helps us to reduce costs, it gives us competence, facing limited battery capacity, and we are sustainable persons. And on the social level, it reduces global emissions and grid infrastructure demands. One support approach are instructions. Another one is access to raw energy information, like we saw on the energy interfaces. But in all energy interfaces, workload is a limiting factor in the energy information processing. So it's important to examine workload requirements and consequences of energy information processing to enhance eco-driving in the end. This concept is often used to describe human information processing in dynamic situations, situation awareness from ANSI. It's a knowledge state of three levels: perception, comprehension, and projection of future elements. It's a prerequisite for decisions and actions, and it's also influenced by the interface design and also by workload, according to ANSI. Another model that describes how humans use interfaces to enhance their situation awareness is a model of Johnson and colleagues. It's important for humans to have the state estimator and to know what are the system states. If we don't know, we have uncertainty about the system states, which leads us, by a variation of the Sept model, to visually attend the interface that provides us with the information about the system state. This again reduces the uncertainty and enhances the situation awareness. And the longer the interface is not fixated, the more the uncertainty rises. And this is okay until a certain threshold of the uncertainty, the maximum desired uncertainty, which would be the time between two fixations under normal circumstances. Every period that exceeds this normal desired uncertainty is associated with additional losses in situation awareness. Taken together, I think that situation awareness is a compatible model to describe how humans perceive energy information and process energy information. When we look at an energy information display, by acquisition and analysis of this information, we reduce our uncertainty and build up our EDA, our energy dynamics awareness, short EDA. This is also influenced by workload, and yes, the uncertainty reduces EDA. I already said that. Important to say is that uncertainty is, according to Johnson and colleagues, a metric that is measured by gaze data, by fixations, by eye movement data. So we ask ourselves, how can we measure the visual attention towards the energy interfaces in an online study? Well, because during a worldwide pandemic, online studies are quite handy and also in general easy to administer, and they have some other advantages. So we thought about occlusion. Occlusion is normally the momentary covering of information or visualizations. And in general, participants cannot control when the occlusion occurs. So more often it's an independent variable when the information is occluded. But when participants can manually control when the occlusion occurs, it can also serve as a data collection method. So we had 3 research objectives in this study project: to build up and test an experimental setting to examine EDA in different workload conditions, to integrate and test the manual occlusion technique in an online study, and to examine the empirical link between the visual attention towards energy information and the EDA, also self-assessed EDA. So we recruited a typical student sample, nothing special here, and we created an online video experiment. So participants saw this video of pre-recorded videos in the inner city of Lübeck, and after they saw this trip, we asked them how accurately as possible they would estimate how many watt-hours per kilometer were consumed on average in this trip. Very difficult question. So for them to have the slightest chance, first they got an energy interface display. This is the trace display we saw before, visualizing the consumed energy and the regenerated energy. And in order for them to have another abstract task, we asked them, after 2 trips on the same route, on these 2 trips, which one was more inefficient, where was consumed more energy. And both energy estimation tasks are supposed to measure EDA by a performance measure. Moreover, we asked the participant to self-assess their EDA by our EDA Scale, which is a bit more subjective measure and aims at measuring all 3 levels of situation awareness by self-rating scales items. The workload was induced by an NBAC task, a visual spatial NBAC task, where they saw this cross on the windshield. One side was the stimulus, and they had to respond by pressing one of the 4 keys, WASD, like in video games. And the 0 back condition was to react directly, and in the 1 back condition they had to remember the one before. They received instantaneous feedback by the color of the cross, the square around the cross. And the manual occlusion looked like this. So there were 2 possible states. First one, the windshield view is visible with the NBAC task. The second state is the energy interface is visible. And the participants could switch these 2 views by pressing the space bar. And by default, the windshield view was visible, so every space bar press was the change towards the energy display, so we could measure the time the space bar was pressed. We had timestamps on that. Yes, and so the uncertainty metric is a gaze data measurement, and important for this is the time between 2 display fixation, and this is what we call sampling period here. We'll refer to this. So overall, there were 2 parts, each with 2 trips and different workload conditions, and in both parts, the gaze data and the sampling period was recorded, the EDA measurements were recorded, and also the NASA TLX as a manipulation check. So first look at the manipulation check. In terms of accuracy in the NBAC task, we see a significant difference between the 2 workload conditions, but not for reaction time. And also for the NASA TLX, in the overall scale we don't see a difference, but when we look at the item 1, which asks specifically about the mental load, we see a difference. So we can assume that there are 2 different workload conditions. Concerning our research objective 1, where we asked ourselves, can we examine EDA in different workload conditions, then first we have to see that the EDA scale does not show any difference in the workload condition, as well as the task to identify the inefficient trips out of 2. They were equally correctly answered in both conditions, so no difference. But when we look at the consumption estimation question, we see that in the 2 workload conditions, in the high workload condition, the consumption estimation was significantly worse, so less accurate. So this is the deviation to the correct value. When we look at the gaze data, the sampling period, we also see a significant difference, which means that the sampling period was significantly longer in the high workload condition. And now when we look at the uncertainty measure, as described by Johnson, this means that there's a ratio, the uncertainty is computed as a ratio between the 2 sampling periods of the different workload conditions to see the additional uncertainty in the high workload condition. And if this is greater than 1, then there is additional uncertainty in the high workload condition. So we tested this, and there's also a significant difference towards the value 1. The last results concerning the empirical link between the visual attention and the EDA measures, we see no correlations. This is just to complete. So this study has some practical and theoretical implications. As practical implications, we were able to test the approach to use manual occlusion as a gaze data collection technique in an online video-based experiment, which is, I think, quite interesting. We tested the approach to use different workload conditions in this online video-based study. And we tested 3 approaches to measure EDA, which was so la la. And in terms of theoretical implications, thank you. In terms of theoretical implications, we see that because the sampling periods differ in the 2 workload conditions, visual attention seems to be influenced by workloads. Also, the comprehension of energy consumption seems to be influenced by workload. And because self-assessed EDA does not show any difference and no empirical relation to the other measures, I think that the self-assessed EDA is conceptually something different than the objective or actual EDA, which I think is a topic that is often not so much discussed in the Ansley models. And this is something I will look at a bit further. For example, in my next study, in the driving simulator study, I just launched a pilot study. I'm looking forward to show you the results of this maybe soon. So in this we can further have a look at the eco-driving implications of these energy interfaces and also try out our measures. Yes, and with that, to conclude, I would like to thank the co-authors Thomas and Mona, and also I would like to thank Hannah Küpper, who did her bachelor thesis in this project, but is not part of the authorship anymore, but also thanks to her, and thank you for your attention.